In this video we're going to look at a hydraulic jack problem, which is a good example of how we can use the laws of hydrostatic pressure in engineering. So what we have here is we've got a hydraulic jack with a piston with an area A1 and a second piston with an area A2, which is larger than A1. We're going to apply a force F1 to the first piston, and then we're going to get a larger force F2 from the second piston. And then in this particular problem, the force F1 that we're applying is 100 newtons. The diameter of the first piston is 0.01 meters, and the diameter of the second piston is 0.2 meters. And what we're expecting is that the force F2 is going to be larger than the force F1 because the diameter of the second piston is larger than the diameter of the first piston. But before we solve the problem, let's have a quick look at what's going on inside this problem. So the two things we have to remember to solve this problem are, first of all, that force equals pressure times area, and therefore pressure equals force over area. That's the first thing we need to remember. The second thing we need to remember is that if we draw a horizontal line across a fluid of the same density, the pressure is going to be the same across the horizontal line regardless of the shape of the container. So everywhere that we put a horizontal line in this jack, the pressure along that line is always the same. So what we know, if we draw a line just under the pistons, we can see that the pressure here, P1, is going to be the same as the pressure here, P2. So we can say that for this system, P1, the pressure under the first piston, is equal to P2, the pressure under the second piston. So, what is the pressure under the first piston? Well, we know that pressure is force over area, so P1 is going to be equal to F1 over A1. We can then ask what is the force coming off the second piston F2, and we know that force is pressure times area, so F2 is going to equal P2 A2, and we know that P1 equals P2, so the pressure under the first piston P1 is also equal to the pressure under the second piston P2, so we can substitute P2 with F1 over A2, so F2 is actually equal to F1 A2 over A1. And what we're saying here is that by playing with this ratio of the area of A2 to A1, we can magnify F1 to make it much bigger at F2. So if, say, A1 was 1 meter squared and A2 is 100 meters squared, then A2 over A1 will be 100, so F2 will be 100 times larger than F1. So now we've got some of those principles in mind, we can go back to the example at the start and we can start to try and solve this. So again, what we need to remember to solve this problem is F equals pressure times area, and therefore pressure equals force over area. So the first thing we're going to do is work out the pressure under the first piston P1. So we know that the pressure P1 is going to equal to F1 over A1, which equals to 100 newtons, which is the force F1 pushing down on the first piston, and then we need the area A1. Well, we're not actually given the area A1, but we're given the diameter of the piston, so the area is going to be pi r squared, so pi 0.01 over 2 to give us the radius squared, and that gives us a pressure P1 of 1273.239.5 newtons per meter squared, and that's the pressure at P1. And we can remember that P2 is also equal to P1. So that pressure under the first piston is the same as the pressure under the second piston. So we can then ask, what is this force F2 going to be? Well, force is pressure times area, so F2 is going to equal to P2 times A2. But remember that P2 is equal to P1, so P2 is going to be what we've just calculated, 1273.239.5 times A2, which again is going to be pi r squared, so pi times our diameter over 2 squared. And that gives us a final force of about 40,000 newtons. And what we can notice by looking at this problem is actually that just by making A2 bigger than A1, we've now magnified the force, so that F2 is actually equal to F1 times 400, so we've increased the force by 400 times just by increasing the area A2.